All right. So we have now reached the point where we have a rocket. We can pressurize it. We've looked at using carbon dioxide. We've looked at using hydrogen. We can correct for water vapor that's formed by reactions because of the evaporation of the water. We are really basically have all the pieces we need to know to deal with mixtures of gases, gases individually, any kind of gas that behaves as an ideal gas, that follows our ideal gas law, PV equals nRT. There are some other things that we want to be able to take into consideration, however. If we have the rocket generate its own pressure, one of the things we have to sort of look for is how long can the rocket sit pressurized? It's likely that the gas might leak out, that there might be small pores in the material, that there might be leaks in the valves. Those kinds of issues are things that we want to be aware of. And in particular, what we're really curious about is how do different gases behave? Does hydrogen leak at the same rate that carbon dioxide does? What factors affect the rate at which a gas would leak out of our container? So clearly the container itself would make a difference, but let's say we have the same container. Does the gas make a difference? These topics, these ideas of gases leaking out are covered by things that we call effusion, which is a gas leaking out of a container. Or if we have two gases mixing, similar idea where we have a gas sort of spreading out, that's called diffusion. So effusion and diffusion are two really important topics that we sort of round out our understanding of how gases behave. How fast do they travel? How do they leak? How do they mix? That's the sort of last bit that we need to round out our ideal gas law. The thing that we still have to do, however, to really help us understand what's going on here, is we really also want to think about, is there some way that we can combine all these different ideas and have some sort of theoretical understanding? Is there some concepts, a theoretical underpinning that will allow us to explain why the gases behave as they do? So far, all the work we've been doing has been empirical. We've simply gone into the lab or read reports of people doing work with, what happens when I press down on the pump. Conducting experiments and seeing what is the relationship between pressure and volume. What is the relationship when you have multiple gases in the same container? These are all empirical laws that are derived from experimentation. But we would like to put a sort of fundamental underpinning around this. And one of the things that becomes really important here is that we do see differences in the way that effusion and diffusion take place based on the size and the temperature that the particles are at. But size is a very amorphous concept. And this gets to the heart of what we consider to be ideal gases. Because when we talk about size, are we talking about the volume of the particles? Are we talking about the mass? What about them? What intrinsic property is important? And so we need to have a bit of a better understanding about what we mean by ideal gases. Okay? So ideal gases, there are a few important postulates, a few things that help us describe how ideal gases behave. Okay? Ideal gases, we assume, travel in straight lines and bounce off following laws about angle of incidence and angle of reflection. But the particles travel in constant straight motion, straight line motion. Okay? So that's one of our postulates. One of the ideas behind the ideal gas law is that particles travel in straight lines and that they're not attracted to their container walls. There's no force of attraction between the particles and the container walls. Second sort of postulate, the second sort of important thing about ideal gases is that ideal gases, that their velocity of the particles or their kinetic energy, more appropriately, is directly proportional to their temperature in kelvins. That temperature in kelvins is a direct measure of kinetic energy. Okay? The higher the temperature, the faster the particles are moving. Okay? But temperature is a direct measure of kinetic energy. Final postulate, or not a final, but the next postulate here is that the size of the particles, their actual volume that they take up, is insignificant compared to the volume that they fill. So if you have a balloon filled with a gas, if you took each molecule and measured its volume, that volume is essentially zero. It's so small that it doesn't matter, that it's insignificant compared to the full size of the balloon. Okay? So, particles have zero volume. Particles move in straight line. Temperature is a direct measure of kinetic energy. Okay? And finally, the particles themselves do not interact with each other in terms of attractive forces. That we only need worry about the particles bouncing around and hitting the walls, it's causing pressure. The particles themselves do not interact with each other. There's no attractive or repulsive forces between particles. These last two are sort of the big ones that we will talk about when we come back from Thanksgiving as being questionable, things that we might need to correct for. But for ideal gases, and ideal gases work really well for normal Earth conditions. Normal atmospheric pressures, normal temperatures. The ideal gas works really well for most gases. Okay? The ideal gas law doesn't work quite as well when you have low temperatures, and high pressures. Okay? When you get high pressures and low temperatures, the volume shrinks of the gas that it occupies, the particles move more slowly. These sort of postulates, these ideas break down. They no longer apply as well, and gases stop following the ideal gas law, and we'd have to use a more complex equations to model what's going to happen. Most of the time we work in the realm of gases that behave like ideal gases. Okay? So, they move around in straight lines. Temperature is a direct measure of kinetic energy. The volume of the actual molecules is negligible. We can assume it's zero. And the particles don't interact. There's no attractive or repulsive forces between the particles. Those are the postulates of the ideal gas law. Those are the things that we can use to explain why gases behave the way they do. So when we do this, the volume we assume is zero. So it's not the volume that's important for thinking about effusion and diffusion, how fast the stuff is going to leak out of our rocket. It's the mass. Okay? Now, particles at the same temperature, gases all at the same temperature, are going to have the same kinetic energy because we said temperature is a direct measure of kinetic energy.
I thought in the first slide that we said diffusion and diffusion depend on size.
Right. What is size? What do we mean by when we say size? And it turns out that it's not volume. The volume is essentially irrelevant, that it's the mass of the particles. Okay? And mass is a measure of size. Right? The word size is ambiguous. It doesn't tell us, it's not definite enough for our purposes. So the rate of effusion, how quickly the gas will leak out, is equal or dependent upon, it's proportional to what we call the root mean square velocity. That is, how fast are the particles traveling? Okay? Effusion is defined as the rate at which gas particles leak through a small hole in a container. Okay? Where the hole is on the same order of size as the particles themselves. Okay? So these are gas particles floating around. They bounce. They hit the container walls. They bounce off. Every once in a while, one hits the hole and escapes. So this rate of effusion is going to be proportional to what we call the root mean square velocity. The root mean square velocity, which chemists use U, RMS, to represent, because we use V for volume, so they use U for root mean square velocity. URMS is equal or proportional to the square root of 3RT over the molar mass in kilograms per mole. This is super important and a place where a lot of people get tripped up. Because of the way the units are structured in here, This has to be in kilograms per mole. And the R value is joules per mole Kelvin. So it's slightly different units, hence the slightly different value, 8.3145 joules per mole Kelvin. It's on the useful equation sheet. Okay?
So if it's in that equation, R is
It's a different value because we changed the units. It's actually the same value. But if you change your units, that changes the expression of this fundamental universal constant. On the useful equation sheet, it's listed in 3 or 4 different ways, actually, depending on what units are used.
So the root mean square velocity is the rate of diffusion.
It's proportional to the rate of diffusion. So it's directly related to it. Yeah, it's not the exact same number, but it's close enough for our purposes. All right, so the root mean square velocity is literally how fast are the particles moving. It's very much like the speed of the particles. And you can see that the speed of the particles depends on the temperature of the particles and the mass. Okay? At a given temperature, all the gases will have the same kinetic energy. Kinetic energy is a measure of how much energy they have because of the way they're moving. But if they have different masses, they will have different velocities. Heavier particles at the same temperature, same kinetic energy, move slower than lighter particles. Lighter particles move faster at the same temperature than heavier particles. Lighter particles will have a higher root mean square velocity and will effuse faster at a given temperature.
Wait, so heavier particles have more velocity?
Heavy particles have less velocity. They move slower at a given temperature. They have the same kinetic energy. Kinetic energy depends on mass and velocity. So if particles have different masses, they're going to have different velocities. Now, one of the reasons that we're learning all about this is, in addition to sort of rounding out our understanding and thinking about how fast will one gas escape from a container, it's also super interesting or useful because we can use it to find molar mass. Now, do you remember, we've talked about this before, doing empirical and molecular formulas? And we said, hey, we have to be able to figure out the true molar mass to find out what the real formula is. So we have to be able to figure out the molar mass without knowing what the substance is. And so far you've learned one way to do that. If you can find the density of a gas, we have an equation that will help us calculate the molar mass. Well, if you can measure how fast the gas is effusing, okay, you can use a ratio between a known gas and an unknown gas to figure out its molar mass, because this root mean square velocity equation has molar mass in it. So here's the thing. Let's say I have the root mean square velocity of hydrogen, and I have the root mean square velocity of carbon dioxide. Remember, we were interested in how are these two gases behaving in terms of our effusion rates from our rockets. So we could set up a ratio between those root mean square velocities. I could take the ratio of the hydrogen to the carbon dioxide, which would mean I'd have a ratio of these square roots. I can do a little hocus pocus and rearrange these things, right? This is an equation that I can rearrange. So I have the square root of 3RT times the molar mass of carbon dioxide divided by 3RT times the molar mass of hydrogen. What's going to drop out there? 3RT. So what I have is now that the rate of effusion, the ratio of the rates of effusion, are equal to the square root of the ratio of the molar masses. So let's say I knew the molar mass of carbon dioxide and the rate at which it effused, right? I have the molar mass and the rate of it diffuses. And I measure an unknown gas. I can measure the unknown gas, how fast it effuses. I'd have 1, 2, 3 parts of the equation. I could solve for the fourth, the molar mass of the gas I don't know. So this is another way, a second way that we can calculate the molar mass of an unknown substance. That turns out to be a really important thing to try and want to be able to do in chemistry. Because if we can figure out the empirical formula and we can figure out the true molar mass, then we can find out the real formula for the compound. Okay? So, which of these gases is going to effuse faster? At the same temperature, what kind of gases effuse faster? Heavier or lighter? Lighter gases. Lighter gases are going to fuse faster. So we know it's going to be hydrogen. The question we want to answer is how much faster? What's the ratio? Okay? So again, we have our rockets, hydrogen and carbon dioxide in here. If we think about a certain amount of time passing, in a certain amount of time, we're going to get 4 particles of hydrogen leaking out and 1 particle of carbon dioxide. Okay? Because of the hydrogen being a lighter gas. So lighter gases will effuse faster than heavier ones. We could actually calculate how much faster if we wanted to. We know the molar masses of each one. We would take the ratio, and then we would take the square root of that ratio. You'll have some homework problems to play with that a little bit. But a much more useful tool to us is to measure to determine the, well, we can go ahead and do that, right? We have this was the equation from before. This is our root mean square velocities and our molar masses. Notice carbon dioxide, right there on opposite sides, bottom and top. So we know the molar mass of carbon dioxide is 44. The molar mass of hydrogen is 2. We can divide that out, take the square root, and find out that the rate of effusion of hydrogen is 4.6 times faster than the rate for carbon dioxide.
These equations with the molar mass be given?
Yeah, for so far. But there are, of course, we would want to also be able to find the molar mass of an unknown substance. And I'll show you an example of that in a sec. Jonathan?
So if you were to, that would be like the inverse if you put CO2 over H.
So if you switch these, then you switch those.
Would these say though you had the define molar mass?
Well, it depends on what information you're given and what the problem is asking you to find.
Oh, because they gave you what?
This problem says use molar mass to find relative rates. So we're asking how much faster does hydrogen effuse than carbon dioxide? Hydrogen effuses 4.67 times faster than carbon dioxide. Yeah, Emma? Okay. So, because if you think, right, I'm going to move the carbon dioxide to the overside, the rate for hydrogen equals the rate of carbon dioxide times 4.67. Okay? So again, if we want to, we can go through and we can use this ratio of effusions to determine the molar mass. Okay? What we're going to need rates of effusion for 2 of them, or root mean square velocities, for each gas, and the molar mass of at least 1 of them. There's 4 parts of this equation, right? 2 root mean square velocities, or rates of effusion, 2 molar masses. I got to have 3 of the 4 variables to solve. So it's totally possible to have an equation like this, right? 2 gases are leaking from the rocket. The first we've identified is carbon dioxide. Carbon dioxide is leaking at a rate of 28.6 milliliters per minute. This is a very typical way to see rates of effusion described. Some volume per time. So how much, what volume of gas is leaking out per unit of time. And then there's another gas that's leaking at a rate of 44.7. Straight off here, which gas is lighter? What do we look for? Yeah, the faster the rate of effusion, the lighter the gas is going to be. So since carbon dioxide effuses slower, it's heavier. Okay? This problem is asking us to solve for the molar mass of the unknown. We don't need to calculate the actual root mean square velocity because it's going to be directly proportional to the rate of effusion. We can use rates of effusion in our equation. In this equation, you can use, instead of root mean square velocity, you can use rate of effusion. So this is the equation right? The rate of effusion, rate of root mean square velocity of the unknown over carbon dioxide, molar mass of carbon dioxide, molar mass of unknown. Okay? I've given you 3 of these 4. Solve for it.
How do you know to put the unknown on top?
It doesn't matter. You can put the if you put the unknown on the bottom, then its molar mass has to be on the top over here. They always are opposite, and that was because if you look back at the root mean square equals square root of 3RT over m, it's over m, and that's why these are always opposite each other. Okay, so take a minute, substitute. There's 3 values here, or from the periodic table. Substitute them in and solve. That's it. The key to really doing these types of problems is recognizing what it is they're asking you to do. When you are given, there's some unknown and you're given some rates of effusion, this equation should be the one that pops into your head. Or that you say, oh, I need to do some sort of ratio with those rates of effusion. Where's my useful equation sheet? Let me look up that equation. Yeah. All right, so have you done your substitution? Where does the 28.6 go? That's the rate of effusion of carbon dioxide. And the 44.7 is our unknown that goes here. What's the molar mass of carbon dioxide? 44.01. So you should have gotten this 44.7 milliliters per minute divided by 28.6 milliliters per minute. Square root of 0.04401. I did convert into kilograms per mole. You don't have to. You could do it in 44.01 grams per mole. That will work because this is a ratio. Okay, because those units would be canceling out. Now, here's what I would do next. I don't want a fraction. I'm going to divide this out to a number. Okay, so I would divide that out to a number, 1.56. Now I have a square root here. The thing I'm trying to find, my unknown, is buried under that square root. I want to get rid of it. What do I do to each side? Square both sides. So 1.56 squared equals 0.04401 kilograms or 44.01 grams. So now I can move the thing I'm trying to solve to the other side by multiplication. Then I'm going to move the 1.56 squared back by division. And I'm going to get 18.02 grams per mole. What does that number seem familiar? Okay, 18 but different point. Yeah, 16 plus 2, right? Or 1 oxygen plus 2 hydrogens. It's water. Does that make sense? What did we have? What did we say were the gases in our rocket? H2O and carbon dioxide, right? Because the vinegar solution was producing water vapor. So, hey, that makes a lot of sense why we would see some water leaking out as well.
So if we had like a problem and we could find the molecular, so we could like find an empirical mechanism.
You will have to do that for homework. Yep. You'll see some practice problems. All right, one last thing. Diffusion. Okay? Diffusion is almost the same, almost the exact same as effusion, but it's a little more complicated. It is, guys, this is important. So diffusion is how quickly one gas mixes through another gas. Okay? The classic example of diffusion is a reaction between concentrated hydrochloric acid and concentrated ammonia. You take a little sample of each, you put it in a glass tube, and then you watch how quickly do the gases move. Lighter gases will diffuse, move through the room faster. Now, they don't move at exactly their root mean square velocity. There's a lot of bouncing around in particles, which is why diffusion is a little bit more complicated. But again, the ratio will work. We can use the ratio of diffusion rates just like we would use the ratio of root mean square velocities or the ratio of effusion rates. Okay? So if we did this, if we started with some ammonia on this side and hydrochloric acid over here, the two particles would volatilize, we'd get gases, okay? And the gas, heavier hydrochloric acid moving slower than light ammonia, and when they hit, they form a solid, okay? They'll hit and form a solid, and you'll actually see smoke forming a ring. If I have time, I will set it up for us next week. If you want to watch me doing it last year or the year before, there's a video of me doing that on the website. But I will try. We have to have fresh ammonia or else it doesn't work very well. So we have all the apparatus. You can watch me do it online if you want. It's a good demonstration. I have two demonstrations I want to do next week. This is one of them, and the other one goes along with a worksheet on determining how do we figure out the gas density to do molar mass. And so I'll probably try and do those two on a demo day next week. Well, in the ideal gas law, what we're talking about is things like intermolecular forces, like attractive forces that like hold a liquid together. Chemical reactions can totally happen. And so, yeah, the ideal gas law says they don't happen, but we all know that that's not true. That the ideal gas law is a construct. It's a mathematical model that works really well for a lot of situations, but it's not reality. Okay? So we can use this distance. Notice how much further, this is the ammonia started here, the white is forming here, okay? The distance that they travel, distance 1 divided by distance 2, is again going to be proportional to the root mean square velocity, which is proportional to the inverse of the molar mass, square roots of the molar mass. It's not quite the actual ratio. This ratio usually turns out to be a little bit different because of influences of the gases bouncing around the air and interacting with other particles.
So distance 1 is that part.
So you can call 1 whichever. If we call the 1 the ammonia, that would be how far did the ammonia travel. And distance 2 would be how far did the HCl travel. Okay? So while we say equals here, it's not quite true for diffusion. It's proportional or about. Okay? Usually for our purposes, it's close enough. All right? So next week, you have several worksheets that I've given you. Next week, we're going to wrap this up. We're going to talk about how can we make the ideal gas law better. How can we make it model real gases a little bit better. Okay? We'll talk about what's known as a van der Waals equation, which is the equation for real gases. It's like the ideal gas law, except it's got a couple of modifying factors that deal with some of those things that we said, hey, gases don't have any real volume. Well, the gas particles do have volume. Gases don't attract each other. Well, they really do. And so we can correct our equation. Makes it more complicated to use, but we can add correcting factors to improve our equation, make it more useful in more situations. But that is a much less important topic for both our test and the AP test. This stuff that we've done is the sort of core material. We'll talk about the van der Waals equation just so you have a sense of, in case it comes up on a multiple choice question, you'd know what those factors do. Yeah, I would think so. All right? All right. Looks like we're ready for some flight tests of our rocket. I was a monkey that they launched into space to test what would happen. People had no idea originally what would happen if you went into space. That's why they sent animals first.
Dogs were the first animal to go into space.
It's true.
She's so excited.
All right.
Great.
Oh, sorry.